Okay, so what we have here is two different polar curves, and if we were to sketch a picture of what these two curves look like, -8 cosine theta is a circle with a diameter of 8, centered on the x-axis on the negative side. And then 4 plus 4 sine theta, this is a limicon. I'm going to write those words down here, circle, limicon. And the limicon is centered on the y-axis, and it looks something like that. And the focus of the lesson today is to talk about the areas enclosed by these curves. Now, there is the potential for 4 possible questions that I can, or maybe even 6 possible questions that I can think of. We could have the area inside the limicon, but outside the circle. And we'll call that region 1. We could have the region 2, which would be inside both. We could have region 3, which is inside circle, outside limicon. And then the 4th one, which I'm not going to write down, would be the total area enclosed by both of them. And setting up the expression for this is going to be dependent on what the question asks us to do. So we're going to start with setting up region 1, which is inside the limicon but outside the circle. Now, if I were to talk about this shape one of the important points to look at is this location where they connect with one another. Because as I fill in this region, if I simply do the area of the limicon, it would grab too much area. So what we're going to want to do is we're going to want to do a chunk of the limicon minus a chunk of the circle. And when we set up our polar expression like that, what we will get is the striped zone only. So let's start with grabbing most of the limicon. Most of the limicon would be this. And we have to know what are the boundaries. And the boundaries for that chunk of the limicon would be from -pi/2 up to alpha. Because when we start drawing this limicon, this is at angle 0. But if we want to get that bottom region, we need to start at angle -pi/2. So right now, this integral expression represents the striped zone and the black zone. So what we are going to need to do is subtract out the black zone. And the black zone would be the region of the circle, that's why I selected radius 1, starting at 0 and drawing out to angle alpha. we of course need to know what is the value of alpha. So if we were to sidestep over here to determine what alpha is, that would be setting R1 equal to R2 and finding the points where those two curves intersect. Sometimes this can be done by hand, and sometimes we need to rely on a calculator. Oops, there should be an equal symbol. This one doesn't look particularly pleasing to the idea of solving by hand. So I'm going to rely on my calculator to find the intersection of these two curves. So when I pull up my calculator, make sure I'm in radian mode. I'm solving a trig expression, so it's nice to do zoom trig on the expression. I'll put one equation as my y1 and the other equation as my y2. And when I draw the graph, I have the blue curve represents the Limousin equation, or the right-hand side of the equation, I should say, and the red curve represents the circle, or the left-hand side of the equation. And I see that we have one intersection point that appears in the second quadrant. When you're in zoom trig, a first quadrant, second quadrant, third quadrant, fourth quadrant. I'm pretty sure that's the window. Oh, maybe a little bit off, but we're going to find that exact location. So I can calculate intersect, and we move the cursor close to where that intersection is and hit enter once, twice, a third time. That theta is approximately 2.498, which I'm going to call alpha. 2.498 is less than pi, which is what we predicted, and it is more than pi halves, which is what we predicted. So our drawing supports what we found for alpha. The second intersection point over here, that represents where they come back together at the polar zero. So if we did that, that should probably be at a value of pi, or, sorry, 3 pi halves. Yeah, because that's when the Limousin hits the center again, 3 pi halves. So this is the setup for evaluating the area of region 1. So okay, now we're going to find region 2, the area inside both. And we've already established that alpha is approximately 2.498, so I'm going to leave that information right here to access. I will again draw the curve because it'll help with the visualization. In that region, alpha, there. And our goal is to find this total area right here, the area enclosed by both curves. What we're going to do is we're going to set up the first portion, which is inside the circle. So So inside the circle would be inside radius 1, and that traces out from 0 to alpha. That gives me the sliver, that is the top half of the piece. To that, I want to add the shaded region that is inside the limison. So I'm doing it in addition of a piece that is inside the limison. So R2 squared d theta. And that starts tracing out at alpha and then finishes at 3 pi halves. And that gives me the lower half of the region. And so by taking these two regions and adding them together, I get the area inside both. Okay, let's look at region 3. Region 3 is inside the circle and outside the limison. So inside the circle, but outside the limison. So we're looking for this area here. There is two different approaches that we could take to this. There's a strictly calculus approach, and then there's a partially calculus approach. So let's do the strictly calculus approach first. We've already established that these curves intersect at alpha. And so if I take from angle alpha to angle pi of the circle, what that's going to do is it's going to give me that much space, and I need to subtract out the black region, or the darker region. So I'm going to subtract that region of the limison, and that region of the limison is alpha to 3 pi halves of the limison. So that's using solely calculus to evaluate the area. We took the circle and then subtracted out a chunk of the limison, or I should say a portion of the circle. We didn't do the full circle. If you had already done part 2, then you could use a bit of geometry, and you could say, I am going to take the area of the full circle, which is pi r squared with a radius of 4, and I'm going to subtract out my answer from part 2. Does that make geometric sense to you? We take the full area of the circle and we will remove the answer from part 2. So going back to part 2, we'll just call this equals answer. And now we've defined the variable as a and s, and we can use that variable here. Because why not? The downfall of this is you're relying on previous work to find your solution, and that's always dangerous. So if we wanted to turn to a calculator, we would probably find these, hopefully, the same answer, same value. Okay, sketching the region here for example 18. Our first radius is 3 sine theta, which is a circle on the y-axis with a diameter of 3. So with a little tick marks provided, we can kind of outline that shape. Not perfect, but... And then our second radius is a dimpled limison. And I'm going to eyeball it. Something kind of like that. It's a really terrible dimpled limison, but the flat spot is on the top half of it there, and then it's kind of a circular shape through there. Okay. And the area that we are looking to find is the area inside the circle and outside the dimpled limison. So the desired area is that region. So there are two intersection points that are going to help us set up our expressions. The first intersection we'll call at angle alpha, and the second intersection is over here at angle beta. And so the first task would be to find where do those occur. And they're going to occur when radius 1 is equal to radius 2. So we'll set up the expression 3 sine theta is equal to 2 minus sine theta. Solve the trig expression. 4 sine theta equals 2. Divide both sides by 4. Sine theta equals 1/2. And go to our memory of the unit circle. And that happens at pi 6 and 5 pi 6, which roughly looks like what I've drawn here. So this supports my understanding of those two angles. Now, to create this region, what we're going to do is first we will take the region enclosed by the circle from those two angles. So the region enclosed by the circle is represented by that integral. And then we will subtract out that little triangular wedge that is, I'll highlight totally in orange. So that little triangular wedge would be defined from alpha to beta, and it is the edge of the radius is defined from the limison, the dimpled limison. So this is the expression set up. You'll notice that the boundary on both of my expressions is alpha to beta. So because the boundary matches on both those, we can collapse it to a single integral expression if we wanted to. Also, due to the symmetric nature of this curve or this region, if we wanted to view it as doubling half of something, so if we went from alpha to pi halves, that would be half of the region, and we can double the half of the region, and that's going to get rid of the 1/2. Which certainly makes the expression a easier expression to operate with. Now, if I substitute in the expressions I do find that it is still a difficult integral expression to do by hand, and I would probably rely on a calculator. 2 times 2 is 4, minus 2 minus 2, yeah. So I would turn to a calculator here because we still got that sine squared, which requires the use of the half angle. It could be done by hand, but the focus here is setting up the expression, evaluating it. That's just a tough integral problem. Example 19, identify and sketch the region 3 cosine theta. So that's a circle on the x-axis, diameter of 3. And 1 plus cosine theta, that is a limicon on the x-axis. Find the common interior. So when I identify the two angles, alpha and beta, I'm going to take a slightly different approach here and recognize the symmetry right away. So that symmetry exists there. So when I go from 0 to alpha, the 2 and the 1/2 will cancel each other out because I'm doubling it. If I do R2 as my radius, what that is doing is it's grabbing that space there and then doubling it. So 1/2 of R2 squared is the triangular wedge. And if I do the same thing for the sliver belonging to the circle, that sliver goes from alpha up to pi. Because the circle starts here and it traces out, not to pi, sorry, to pi halves. That spot happens at pi halves. This captures the common interior. We do need to find the value of alpha by setting the two equations equal to each other. Cosine of theta is equal to 1/2 at pi thirds and 5 pi thirds. So alpha is the first instance of pi thirds. Which makes me realize that on the previous example, I never did actually specify that alpha was pi 6, but beta was 5 pi 6. Pi 6. Again, I don't think I would wind up doing this integral by hand because it is slightly challenging. But That's the integral for the region. That came from me doing too much at once. It should be pi-thirds. Thank you for pointing that out. It's because I jumped back to the previous problem for a second. This gives me the total area as we dealt with the doubling.